Hello everyone, my name is Talal Bhutta and today I'm going to talk about Assignment 9, which is a summary of all the assignments we did throughout the semester, starting from our hull design all the way to costing, man hours required, and at the end, network diagrams, etc. My name is Talal Bhutta. Our group mates are Alex Maldonado, Piero Risi, Brianna James, Victoria Nunes, and Sai Karthik Dandamundi, and we are Group 4, the NextGen engineers. Let's start off with what we did in Assignment 1.
Engineers was tasked with creating a research vessel for the Texas Wildlife and Parks Department, in which our mission is to provide a vessel configuration to meet the Texas Wildlife and Parks Department in terms of marine research, finances, and usability. Now, the method that NextGen engineers used to provide this vessel is we created a chart for all the possible vessel configurations using our weighted score and factor score. The factors were determined based on characteristics and they were given a score from 0 to 10. So based on the little chart on the side, the factors and the weights. Based on the background information from the Texas Wildlife and Parks Department, we decided to weight the cost of production, reliability, cost of operation, and operation conditions as the most significant factors in the vessel, especially since the Texas Wildlife and Parks Department is a public entity with limited funds, but their work is of importance. Using the formula provided, where we're multiplying the constraints times the weight and the factor score, we were able to create a configuration based on our chart in which we decided that in order to best meet the needs of the Texas Wildlife and Parks Department, we would create a vessel that is 34 feet, uses aluminum hull, uses a single diesel engine, and a half cabin. This configuration was the most effective at satisfying all of our factors in terms of their weight as well.
For our immediate need for an organizational structure, we chose mixed. A mixed organizational structure combines elements of both functional and project-based models. In this setup, employees report to both a functional manager who oversees technical expertise and a project or product manager who focuses on specific deliverables and deadlines. This dual reporting system encourages collaboration across departments, improves resource flexibility, and promotes knowledge sharing. However, it can also lead to conflicts in priorities and unclear authority if not well managed. When executed effectively, a mixed structure allows organizations to remain agile and innovative while still maintaining specialized expertise, making it a popular choice among industries. For a long-term organizational structure, we decided on peer project. A peer project organizational structure is designed entirely around projects. In this model, teams are formed specifically for each project, and all members report directly to a project manager. The project manager has full authority over the team, budget, and resources, which enables quick decision-making and strong focus on project goals. This structure is ideal for large, complex, or high-priority projects, where dedicated attention is critical. However, it can lead to resource inefficiency and duplication of roles, especially once the project ends, since team members may have no clear path for reassignment. Overall, a peer project structure offers strong accountability and clarity, but it requires careful planning to manage long-term resource utilization.
Once we have the vessel configuration, we further broke down the vessel into its core systems, which we have listed here, the propulsion, electrical, etc. And within each system, given our already chosen vessel configuration, we identified which items might be needed in building the boat. And doing this, we were able to get a rough price estimate on the parts through market research of what's available right now. And so we were able to get an estimate on the overall price for constructing a vessel of our chosen configuration. Once we completed these market research for each subsystem, here we have an overview of what we came up with. As far as the costs go, as you can see, the majority of the costs come from the proportionate hull, since these are the two biggest overall subsystems in terms of weight and just complexity. Um, the hull will need uh, quite a bit of aluminum just to construct the overall skeleton of the vessel, and the propulsion will need to order an engine from our chosen manufacturer, which can get expensive.
Yeah. Hello everyone. I'll be giving a quick recap of assignment 4. We start at the top with the overall vessel project, which is divided into several major components. First, we have plant system design, which includes key systems such as hull construction, propulsion, electrical, freshwater, sanitation, and navigation. Essentially, the core subsystems of the vessel. Next, the construction, which mirrors the same subsystem but focuses on the actual implementation and integration. The third is legal and regulatory, where activities like licensing, permit acquisition, and license issuance are managed. This ensures that all design and construction follow compliance requirements. Then comes the labor agreement, which covers collective bargaining, agreement negotiation, and finalizing, critical to aligning workforce terms before and during the construction, where land acquisition follows, which involving identifying available property, zoning checks, price analysis, and financing. And when it comes to the testing side, we have both system testing and acceptance testing, each with the structured plans and formal validation steps to ensure the vessel functions as intended. Finally, the startup marks the project transition into operational readiness after successful testing and sign off. Now, the second slide, where I added the link of the Excel sheet, which supports the structure with the detailed data like including costs, timelines, system performance metrics for these tasks. And these data sets complement the breakdown by providing the quantitative foundation behind the project plan. Thank you.
Assignment number 5, what we did was project budgeting. And basically, initially, what we did was calculated the amount of hours required for professional man hours, skilled man hours, and unskilled man hours, how much each department would take to assemble the parts and read the whole together. So we got that total number, and then we created a weekly budget combining the hours with the labor cost. And the next thing we did was we created a bill of material and a cost per week, essentially dividing those hours up into 20 weeks, which we are given for this project, and allocate how much amount is going to be used in what week and what weeks are going to be without any cost whatsoever, as you can see on the first picture on the top. Then we got the overall cost, essentially the labor, the supplies that we need, the subtotal, and indirect costs. And indirect costs include renting out equipment and renting out a lot of other things, renting out warehouses, places where we can assemble the whole thing. So, in conclusion, our total budget was about 155,865, from which the material budget is 170, indirect costs are about 10K, so the subtotal is about $661,000.
For assignment 6, I focused on building the network diagram, which maps out the sequence of project activities and their dependencies. This layout helped identify the critical path, the longest sequence of dependent tasks that directly impacts overall project duration. Any delay in the tasks on this path will result in a delay of the entire project. This diagram was kept within 40 to 60 nodes to maintain clarity and ensure manageability. And each node included detailed value calculations. Around each node had the calculations as well for the LS, ES, EF, and LF. By laying it out this way, we're able to see the full project flow and better understand how timing and coordination play a key role in staying on schedule. After analyzing the diagram, we identified the critical path. So take a look at the critical path here. This path represents the longest sequence of tasks that directly determine the overall project timeline. And within the table here highlighted is the zero slack, which means any delay here will push the entire project's completion date. So in this case, the order hole materials and fabric hole both had zero slack, and highlighting this path helped us know which tasks to prioritize so we can keep the project on track and avoid costly delays.
Here we have the crashed network for our project. This is actually a zoomed in network diagram, um, zoomed in on the critical path so that we can see where we were able to save some days on the original schedule. As you can see, there's a few days here and there on each task, adding up to about 21 days that we were able to save from our original uh, schedule. And from crashing our project, we of course had to account for all the additional costs arising from cutting the amount of time that we had originally planned on working on the project. These costs include overtime, additional hiring, additional equipment that might be needed, such as CNC equipment for cutting aluminum, etc. All these costs added up to about $37,000. Um, though we were able to cut around 21 days, so um, we did manage to cut a significant amount of time, though the cost was also rather significant for that achievement.
In comparing the original and leveled schedules, the key difference lies in how labor was distributed over time. In the original schedule, we saw frequent spikes in labor demand, which led to multiple hiring and firing events. This created instability in the workforce and increased costs, especially from onboarding and termination. With the leveled schedule, we use slack and non-critical tasks to redistribute work more evenly. This helps smooth out the peaks in labor demand, significantly reducing the number of hires and layoffs. The result was a more stable schedule with the same total man hours and project duration, but with lower labor transition costs and better resource utilization. When we look at the network differences between the original and leveled schedules, the overall structure and critical path remain unchanged. That means the project timeline and sequence of essential tasks were preserved. However, in the leveled network, we adjusted the start times of several non-critical tasks, those with available flow or slack. These shifts allowed us to better distribute labor across the timeline without delaying any critical activities. This strategic use of slack didn't affect the final delivery date, but helped us minimize idle time, reduce labor transitions, and create a smoother, more efficient workflow, while also saving $7,000 in hiring and firings.
This brings us to the end of our presentation. It was a summary of all the assignments that we worked on throughout the semester, which made us assemble everything essentially from starting of designing the hull to creating work breakdown structures, Gantt charts, and then at the end to network diagrams, try to make it a more efficient process. That's exactly what we did throughout the whole assignments, and we learned a lot. And now we know how to construct a hull. Thank you so much for watching, and that's all, folks.